طيب بسم الله الرحمن الرحيم. So last time we talked about real-time protocol. We talked about the issues in UDP and TCP, which does not make them perfect candidates for multimedia applications, and therefore we need other types of transport layer protocols. So we talked about real-time protocol, and we said that the main characteristics of RTP is to provide payload type, where we describe the encoder that the source uses to encode audio or video. We also talked about packet sequencing, which is used not for retransmitting the packets, not to provide reliability, but only to detect that there are some packet loss, because we need this to adjust the play out time at the receiver side. So the packet sequencing is not to provide reliability in that case, because we said that this feature is not needed for audio and video applications. And also synchronization, which are facilitated using two fields, the timestamps and the source synchronization identifier. So today we're going to talk about the RTCP, or real-time control protocol, and as the name suggests, it actually works in conjunction with RTP. So RTP and RTCP, they work together. Basically, RTCP provides the control messages that are required for multimedia applications using RTP. So basically, RTP provides the data stream, and RTCP provides the control stream. Okay? So RTP is typically used for, as we said, for streaming stored audio and video content, or for video conferencing. So for video conferencing in general, we have one source on multiple receivers. Okay? So in that case, as we said before, we don't need 100% reliability for multimedia applications, but we still need some kind of flow control in a way. Okay, so we need to control the stream rate so that we get adjustable and good quality of audio and video. So this is required, although we don't require reliability, but we need some kind of flow control. So RTCP provides the way for multimedia applications to synchronize audio with video, and to provide some flow control for multimedia applications in order to get constant or consistent quality. So each participant in the RTP session periodically sends RTCP. And RTCP is sent as reports. So each receiver sends a report to the sender, and the sender sends a report to all the receivers. And these reports facilitate the flow control, as well as providing the synchronization for all the multimedia streams in order to provide consistent quality. So each RTCP packet contains sender and or receiver reports. The reports from the receivers, they notify the sender that they have received specific number of packets successfully, which means that there are some packets lost. So using the packet sequencing, we can identify which packets have been lost. Okay? So the receiver informs the transmitter the number of packets sent or the number of packets lost, for detecting the packet loss, not to recover these packets. That's not the objective. The objective is just to detect that these packets have been lost. Okay? But retransmission is not in the scope of RTP. So feedback can be used to control the performance. So the receiver, when it sends a notification or a report to the sender might use that report to adjust the transmission rate up or down. So that's a primitive type of flow control. It's not as rigorous as TCP, because TCP, when it receives one packet lost, as we said, it drops the rate down by half and then it starts to increase slowly. So this type of congestion control, which is really aggressive, it actually affects the quality of the audio and video, as we have discussed last time. So here, there is the flow control is not as aggressive as in the case of TCP. And it's facilitated through the RTCP reports from the receivers to the sender. And the sender uses the number of packets received and the number of packets lost in order to adjust the rate. And it adjusts the rate by small factor up or down. But generally speaking, it's consistent. So the sender may then modify its transmission based on this feedback. Okay. So basically, this is how the scenario looks like. So in a typical video conferencing scenario, we have one sender and multiple receivers. Okay. So typically, we use multicast. Okay, to send the audio and video from the sender to all receivers using one multicast session. So periodically, and we will find out how often this report gets sent, periodically each receiver will send independently a receiver report, okay, using RTCP payload or RTCP control message. Okay, so RTCP defines set of messages. These messages are control messages. They do not contain any data. They do not contain any audio or video. Okay. So for any multimedia session that is going on, there is one session stream which is uses RTP, and this contains the So this is the sender, and this is the one of the receiver. Receiver 1, receiver 2, and so on. So each multimedia application provides RTP session and RTCP session. Okay. RTP contains the data, and as we said, contains timestamping, packet sequencing, and all what we have talked about last time. RTCP provides only control messages. It does not provide or contain any data. The types of data in the RTCP are either receiver report, sender report, or something called sender description, which we will talk about, or some other packet types which we don't care about. Okay. So these messages get sent periodically over the RTCP session, which is separate from RTP. It's on different port. It's on different UDP port. So it's separate in a way from the RTP session. Okay? As we said here, so RTP and RTCP packets are distinguished from each other via distinct port numbers. So they are sent on separate UDP sessions. So we can separate them from each other. Okay? Any questions? So the receiver report message type contains some information like fraction of packet loss. So RTCP performs some measurements similar to the measurements that we have talked about that you will probably try to implement as part of your assignment or as part of the course project. It tries to count the number of packets lost for every duration of time, and then it reports the packets lost, the last sequence number, and the average inter-arrival jitter as an average over this whole duration. And then every duration, it provides this statistics as a receiver report. The the other sender report packets, it sends the SSRC, because as we said, each RTP session has an RTCP session that corresponds to it. So this RTCP session will identify what is the stream identifier and the current time. And this current time, as we will see, is an absolute time. We will see in a minute. And then the number of packets sent. So from the number of packets sent and from the number of packets lost, using the sequence numbers, we can identify which packets have been lost. Okay. So based on the analyzing the sender report and the receiver report, we can then adjust the play out time. We can then adjust the data rate from the sender side, either up or down slightly. Okay, not as aggressive as TCP, but we can increase the transmission time slightly or decrease it slightly based on this feedback. At the beginning of the session, usually the sender sends a source description packet, and this usually happens at the beginning of streaming the multimedia content. Okay, so this is as if the sender is introducing itself to all the receivers. Okay, so this is the sender, and my email address is so, and the host name is that, and I'm gonna send this set of streams, and the source description packets provide some mapping between each stream identifier and the host name. So we know that this host is sending those streams, whether this is an audio stream and a video stream and so on. Okay, so typically we have one sender which sends RTP for audio and RTCP for audio, and there is RTP for video, and there is RTCP for video. Okay, so there is one source description packets that gets sent over the RTCP sessions to map all these SSRCs, because each one of these provides an SSRC, which is the source synchronization identifier, okay, for RTP, for one RTP stream. So the source description packets, it gets sent over RTCP sessions to identify that these SSRCs, they belong to this host name. Okay, so this way the receiver can group all the streams that came from a particular host name. This is coming from the same source or the same host name, and it tries to merge audio and video and other streams together, and then it uses that for synchronization between audio and video, and we will see how this happens. Okay, so the source description package gets sent at the beginning of the session to introduce the sender to all the receivers, and then periodically we send the receiver reports from the receiver to the sender, and the sender report from the sender to all the receivers. Okay? So any questions so far? Okay? So that's the sequence. So there are two major functions for RTCP that we will talk about now. The first one is synchronization. So we talked about the fact that RTP provides timestamping and provides source synchronization identifier. Okay? Using source synchronization identifier, we can group set of packets to say that all these group of packets, they belong to the same stream. Okay? Using multiple SSRCs, we can say that these packets belong to an audio stream, these packets belong to a video stream, and then we use the timestamps to synchronize each of these packets together. So this way we can play out the audio and video consistently at the receiver side. Okay, so that's how we group the packets that belong to the same stream. And then the source description packet groups multiple streams and map them to one host. So the way it goes is that first we have a host. Each host sends multiple streams. Each stream is identified using the SSRC. And then within one stream, we put timestamps in each packet that we can use for synchronization. So RTP provides this information, and RTCP performs the actual synchronization. So RTCP can actually synchronize these different media streams within the RTP session. So RTCP provides the synchronization between the audio and video stream. So the timestamps in the RTP packets tied with the video and audio sampling clocks. So remember that timestamps that we have talked about in RTP are defined based on individual logical clocks in each stream. And these logical clocks are just like a counter. Okay? So for us, we start at 0, then we count a clock, and then the next packet will be after like 100 clock cycles, and then 200 clock cycles, and so on. Okay? Whenever we have multiple clocks, we need some kind of a reference clock that is used to synchronize these streams together. So we have a source. We have one RTP1, which is for audio, for example, and this RTP1 has timestamp 1. Okay, and we have RTP2, which is, for example, video, and this one has timestamp 2. Okay, so RTCP in that case uses what we call a wall clock. A wall clock is an absolute time, okay, which is used as a reference time for both RTP1 and RTP2, or in other words, timestamp 1 and timestamp 2. So in that case, it says that pay attention to the fact that TS1, the first packet in that stream, was generated at time 12.1230 or something like this. Okay? So this actually maps the individual timestamp, which is based on a logical clock for that stream. It maps it to an absolute time. So this absolute time is then used to synchronize the individual packets from stream 1 and stream 2 together. Okay? So the timestamps that RTP has are not enough to synchronize. Okay? Then RTCP is needed to provide a wall clock, which is a reference clock, together with the timestamps in RTP. Those two are both needed to facilitate the synchronization. ماشي كده؟ مفهوم؟ So yes, the wall clock is an absolute time. The timestamp in RTP is not an absolute time. It's a relative time, relative to the clock that's provided or that's used by that stream. Okay? But then RTCP says, pay attention to the fact that this reference time is based on this time. And it needs to send the absolute time again periodically, not with every packet. So I just need to know that the first packet, which the timestamp for which is let's say 2, this corresponds to a time 12:30 point something. Okay? So this way, if there is a packet that's at timestamp 100, so we know how to calculate its absolute time based on the wall clock. So the wall clock is sent periodically, and together with the timestamp in RTP, we can get the absolute clock for every packet. Okay? Because the timestamp that's contained in RTP is relative. So RTCP sends the absolute time based on which we can always calculate the absolute time of every packet based on this wall clock. Okay? So in other words, we need both timestamp inside RTP together with the wall clock from RTCP to provide full synchronization.
Doctor, why do we have to do all of this? Why can't we just use the real clock?
Because I think because the real time is long to represent inside each packet. So it's quite an overhead. So instead, what we do is that we use a relative timestamp inside each packet, which is a normal 32-bit number, and then we periodically, every now and then, and we will see how often, every now and then we send the absolute clock or the wall clock. So this way we can get the relative timestamp, and based on the wall clock we know the actual absolute time of each packet, and we can not only know where this packet is played out, but we can also synchronize this packet with other packets in the other streams, because the wall clock is relative to the host itself. So this is a common time for all the streams, not just one stream. This is a common time for all streams. Okay? So we can use it to provide complete synchronization between audio and video. Okay? So each RTCP sender report packet contains information like the timestamp from RTP and the wall clock. And the timestamp from RTP is the timestamp for each for the first packet. Okay? And the wall clock, which is the absolute time. So I know that the packet that is sent at timestamp 2 was in fact sent or was generated at time 12:30, whatever. Okay, so based on this wall clock, I can calculate the absolute time of all the incoming packets. Okay. So the receiver uses this association between the timestamp and the wall clock to synchronize all the packets from all the streams at the receiver side. Okay, so it knows that it will not actually play out at the exact wall clock that this packet was generated, because of course there is a delay over the network, right? So it cannot actually play the packet at the exact time that it was generated, right? It cannot, right? But it knows that if it shifts for like 2 seconds or something, then it shifts all the packets for 2 seconds, and it knows the relative time based on which it can provide the consistent play out at the receiver. Okay? So then the receiver uses the host name to associate all the SSRCs to a particular host, and then associates all the packets that belong to each stream using SSRC, and then uses the timestamp and the wall clock to synchronize the streams together. Okay, so these are the levels that the receiver uses to synchronize. Any question? Okay. So RTCP bandwidth scaling, that's an interesting thing, that it's a fact that RTCP usually attempts to limit its traffic to 5%. So that's the figure based on which we know how often each report gets sent. Okay? So if we want to know how often we should receive whether a receiver report or a sender report, that's the number. That's the only number. So based on that number, 5%, we know how often. And we'll, as an example, suppose we have like one sender in a video conference which tries to send an audio video streams with a rate of 2 megabits per second. Okay? So this way, RTCP will limit itself to 5% of this data rate, which in that case is 100 kilobits per second. So 100 kilobits per second is actually 5% of the 2 megabits per second. Okay? So this is the rate that the RTCP will use to limit the data rate over the RTCP sessions. Okay, so now, remember that we have one sender and multiple receivers. So this rate is actually the collective rate for both the sender report and for the receiver report over the RTCP sessions. Okay? So this rate is actually the collective rate for all the sender and the receiver reports. RTCP gives 75% for the receiver report versus 25% for the sender report. Why? Because typically we have multiple receivers and one sender. So the sender only needs 25% to send the sender description packets and to send periodically the sender report. Okay, so this is the 25. So 25 of the 100 kilobits per second. So we know that the rate for the sender report is actually 25 kilobits per second. Okay, so 25 kilobits per second. This means that we have around, so every 1 over 25, we can send 1 bit, which means that if the packet itself for the sender report is L, so every L over 25 millisecond, we send 1 sender report. Okay, so if the rate is 25 kilobits per second, this means that every 1 over 25K, we send 1 bit, right? If the length of the sender report is L, then every L over 25K or L over 25 millisecond, we can send 1 sender report. So this is the enter transmission time between each sender report.
Again, why it's 25%?
25%, this is given. So 25% is the typical percentage of the sender report versus the receiver report. And we said that why is it not 50-50? Well, actually, for the case of one sender and one receiver, it might be 50-50. But typically, it's 75 versus 25 because typically for video conferencing, you have one sender and multiple receivers. So if you have multiple receivers, it makes sense that the receiver report will be more often because the 75%, as we will see here, it's divided amongst the number of receivers. Okay? So, but you know how we got this number, right? So if you send with a specific rate, if you get 1 over this rate is actually the time that you send one bit. So if you have a packet of length L, then you know that every this number of seconds or milliseconds, we send 1 sender report. Okay? So we have on the other side 75 kilobits per second, which will be equally shared amongst all the receivers. So if you have R receivers, so typically you have 75 divided by R kilobits per second for each receiver. So each receiver on one RTCP session will send a rate of that much. So at every what time we send one receiver report, we get the inverse of this number, so R over 75, and we multiply that by L, which is the length of the packet, and this will be in milliseconds. So the receiver knows that every this number of milliseconds, we have to send one receiver report on the RTCP session. So by controlling these numbers, we can control the aggregate rate for RTCP sessions that are coming from one host to multiple receivers, all to around 5% of the actual data rate of the multimedia content. Okay? Any questions? Is that clear? So we call this bandwidth scaling. So RTCP tries to control the bandwidth by limiting this number. This is a relatively weird way that any protocol can use to control the data rate. So usually protocols, they require consistent frequency of sending the transmitted messages. But this is an interesting way of that's really special for RTCP to provide frequency of sending the control messages. So basically, this is only for control messages. So the data itself is consistent using the 2 megabits per second, but this is only for RTCP, which means that RTCP requires an overhead of 5%. So RTCP tries to maintain its own overhead within 5%. Okay? And it actually dynamically changes the rate over each RTCP session to contain or to limit the aggregate overhead for RTCP within 5%. Okay? Any questions? So that's basically how RTCP works. And as we said, it's a control protocol which works in conjunction with RTP because RTP provides the data part. So RTCP provides the control part, which together with RTP can provide or facilitate synchronization, can provide packet sequencing to detect the packets lost, and can provide some encoder identification to recognize what encoder has been used to encode audio or video, and we have the flexibility to change that over time if needed. Okay? So these are RTP and RTCP. So as a quick introduction to another application layer protocol that's used for streaming. This the streaming stored multimedia. This is an application level streaming technique. So we talked about RTP and RTCP. This is from the transport layer point of view. From the application layer, we can provide some control over the stored multimedia content. For example, when we watch YouTube, sometimes we say pause, and sometimes we can rewind, sometimes we can move forward and move backward and stuff like that. So RTP and RTCP, while it can provide some way to detect that there is a pause, how can we detect that there is a pause for RTP and RTCP? Well, if there is a pause, this means that the sender will not send any packets during the pause time, right? Which means that no packets will be transferred to the receivers within the time of the pause, right? So we can identify this by the packet sequencing, because there will be so for example, this is the sender, and the sender is sending packets in a time frame, and there is the receiver, and the receiver is receiving these packets. So the first packet will be sent and received by the receiver. So we know the packet sequence, let's say, is 1. So we receive packet 1, so we know that this is packet 1. So if we receive packet 3, for example, we know that there is a high probability that packet 2 has been lost. So if we don't receive anything for a duration of time, okay, then we receive another packet. So this packet is packet 2. The timestamp for this packet will be further away, right? The timestamp will be high because it represents, the timestamp will represent this duration, okay? But the packet sequence will be 2. So when I receive packet 2, so I know from the timestamp that it's far down, but I know from the packet sequence that it's a continuation of the same stream. Okay? So in a way, I can detect it indirectly. But the receiver needs to have the way still. When the user clicks on pause, I need to send a command to the sender to stop generating the packets. Okay? And if the user, for example, clicks on feed forward or backward or something, I need to send these as commands to the sender, okay, to control the generated packets from the sender to all the receivers or to one receiver, right? So this is not part of RTCP and RTP because this has nothing to do with the transport layer. This is a control commands that are sent from the application layer. So that's what we use some application level streaming techniques to send these commands between the receiver and the sender to provide some interactivity. Okay, so interactivity in that level, in that case, is interactivity for a stored video content because there is another interactivity based on, like for example, telephony, like IP telephony. So in that case, it's live video streaming, and the interaction happens naturally between the sender and the receiver, but it's not for a stored multimedia content. So the user can interact with a stored multimedia content and can feed forward or feed backward or pause or stop and stuff like that, only for a stored multimedia content, but not for live video telephony or something like this, right?
Even when we pause the video, the receiver will keep receiving packets. The video will continue loading.
No.
On YouTube, when we pause the video, can be loading.
Yeah, it depends. It depends on YouTube. And again, if you try it now, it actually, well, remember there is a de-jitter buffer, right? So it used that time to fill the de-jitter buffer, but not to play out. So theoretically speaking, the sender should stop sending packets. We can allow to send packets for a small duration of time to fill the de-jitter buffer, to facilitate the play out if the user clicks on play again. And in certain percentage of the time, you stop, you pause, and then you wait for some time, and then you may click stop. In which case, you have loaded all the entire stream for nothing. And in fact, YouTube, they have realized this, and for many of the streams right now, if you pause, it will not continue loading the video to the end. It will actually store some duration of the video, but then it will stop. And this duration, it tries to fill the de-jitter buffer. It's not to load the entire content of the video. So the only way to, in most of the time, in some, depends on the server you are streaming from. So for some servers, yes, it loads the entire stream. So it depends, but it's not consistent. Okay. Okay. So as we said, so we use the de-jitter buffer to do some jitter removal. So we'll talk about this. We can, at the receiver side, we do some decompression for the compressed. Remember, for the uncompressed, we don't have to decompress, right? For the uncompressed, using like format like PCM, pulse code modulation, we don't need to do decompression. But for stored video, like MPEG-4 and stuff like this, we still need to go through some decompression. And that's that's an overhead at the receiver side. There is some error concealment. So for the packets that are lost, how do we account for this at the receiver side? So we need to provide some error concealment technique. And there is, of course, graphical user interface to represent the multimedia content to the user. So there is the de-jitter buffer is facilitated or is smoothed out using the client-side buffering. And then we use UDP versus TCP, and for each one of them we talked about different issues. For UDP and TCP, UDP does not provide anything, TCP provides everything, and we don't need either. We need something in between, and that's why we need other protocols like RTCP and RTCP to get us to the consistent quality that we want. And there is multiple encodings of multimedia which we can identify using RTP and RTCP. So now, from the application level point of view, as we said, we need some level of interactivity from the user side. So for example, this is the typical streaming example from YouTube or whatever. So you have a web server with the audio or video content, and we have web servers, and we have media player at this server. So each of these gets designed with certain parameters based on which we can control the play out time at the client side. And if there is some de-jitter buffer, what is the buffer size? Okay, and this actually gets calculated using some complicated equations. It's not that straightforward, because on one side we don't want to store huge amount of content at the client side. On the other side, if we actually store less amount of multimedia content, then we will not be able to compensate for the jitter that's introduced by the network. So in which case, we don't get consistent quality at the client side. So we'll talk about some techniques related to how we resolve this, inshallah, next time. So I think in the remaining time we'll